Hi, in this video I will be solving two examples, but I will be involving the dielectric material within the two plates. So let's see how we can handle the situation of having a dielectric. Now the first example says a parallel plate capacitor has an area of 10 centimeters squared and plate separation, the distance between the two plates, is 5 millimeter. A 300-volt battery is connected to its plates. If neoprene, it's a dielectric material, it doesn't matter if you know it or you don't, it's a dielectric material, is inserted between its plates. How much charge does the capacitor hold? Okay, now things we need to keep in mind when we're solving such a problem. What we do, first of all, our formula will be the capacitance equal the kappa, or the dielectric constant, epsilon naught A over D. And this amount in the bracket represent the original capacitance of the capacitor before inserting our dielectric, which is we could calculate separately then involve it in this equation, but it's not a problem. Now, first of all, we need to focus on the area. It's already given as 10 centimeters squared, so we have to convert that to a meter squared. So the area will be a 10 to the power minus 4. That will be in a meter squared. Now for the distance, again, it will be 5 10 to the power minus 3, and that will be in meter. So we convert it from millimeter to a meter. Okay, now the epsilon naught, we said it's a constant and it is 8.85 10 to the power minus 12, and we know the unit, it is coulomb square per Newton meter. Now let's try to do the calculation for this situation. So the capacitance of this capacitor while we have the dielectric, it will be 6.7, and this number we can see it in our picture here for the dielectric, 8.85 10 to the power minus 12 multiplied by the area, which is a 10 to the power minus 4. All that will be divided on the 5 10 to the power minus 3. Okay, let's do some calculation now. That should give us 1.18 10 to the power minus 11 farad. That will be the capacitance of this capacitor, but the question asking for how much charge. Now, how much charge can be stored in this capacitor? Once again, we know the Q will equal the capacitance multiplied by the voltage. Now, I do have the capacitance, which I wasn't before, -11, and the potential difference across the two plates was 300 volt. Once again, do some calculation. So 300 times, that will give us 3.56 10 to the power minus 9 farad, or you can say it is 3.56 nanofarad. And that will be the capacitance of this capacitor after inserting our dielectric material. Now, I'll leave that to you to confirm that this capacitance of of this capacitor has been increased. If you try to calculate the capacitance without having the dielectric, so just you use the K or that kappa as 1, and you calculate the epsilon naught times the area divided on the distance, you will find that your capacitance with a vacuum definitely less than what we've got now with the dielectric, which is confirming again the job of having a dielectric material within the capacitor's plate to increase the capacitance of a capacitor. Okay? All right. The second example, we have a capacitor made of two square plates with side length 3 centimeter separated by distance of 1 millimeter with air in between the plates, right? So we know the dielectric material, it will be air, so the kappa will consider as 1. The capacitor has a voltage of 100 volt and it is not connected to a battery. So we can say, all right, this is my two plates and they are squared. That's the other plate here. They are connected with the battery. Okay. Now we did charge our capacitor. We know that they are square and each side is 3 centimeter. And we know the separation between them, it's 1 millimeter. We managed to apply 100 volt across the two parallel plate. But after we did that, we disconnect the battery. We disconnect our battery with the capacitor. So I can make an open circuit here, or I can just say, all right, I removed this battery. Oh wait, sorry, we took off part of our plate. Okay, so that's the distance between them. It's 1 millimeter. Okay, so my capacitor is charged, is not discharged. So let's see what the question asks. Now it's telling me to determine the capacitance of this capacitor. All right, that should be nice and easy one. So the capacitance will be the permittivity multiplied by area over D. That will be 8.85. Now the area, well, it's a square. You know that square, we multiply the sides. That will, and remember to convert, that will make it 9 10 to the power minus 4. And you divide it on the distance, which is 1 10 to the power minus 3. That will give us okay, that will give us 7.96 picofarad, and the pico is 10 to the power minus 12. All right, so we know how much is the capacitance of this capacitor when it's filled with air in between the two plates, and this is the situation. Now the second part, he's saying determine the new capacitance if an insulator with a dielectric constant of 4 is added in between the plates. All right, here's the game change. So somehow we managed to insert an insulator, a material, some sort of material between my two parallel plates with a dielectric constant equal 4. Now I need to know the new capacitance of my capacitor. All right, so I could say C dash, or I can say CD to represent dielectric. It's up to you how you present that value. Now, well, we know that the C, the capacitance with the dielectric, can be written like this, or I can do it as a kappa multiplied with the original C naught, the original capacitance. So in this way, just to follow the samples maybe from other previous videos. That is will be 4 multiplied by 7.96, 10 to the power minus 12, and that should give us it is 4 times 31.8 again picofarad, and we can see again that the dielectric material really did increase the capacitance of our capacitor. Okay, now the third part of this example, I can answer it here. He's saying determine the new voltage. Okay, now the key of this one, that this battery or this capacitor is no longer connected with our battery, so the amount of charges will remain the same. So what I can do, I can derive the formula to solve this problem. So we can see, okay, we know that the capacitance with the dielectric equal K or kappa multiplied with the C naught. Now we know this is going to be Q over the new voltage equal K Q over the voltage, the initial voltage when it was 100 volt. Now we said because the battery is not connected, there will be no more charges will be delivered. So it is the same amount of charges before and after disconnecting the battery. So these Q's will disappear, which means I will have this magical formula where the dielectric or the voltage of a capacitor with a dielectric equal the initial voltage divided on the dielectric constant. From here I can solve how much is the new voltage of my capacitor. It is 100 over 4, and that will give me 25 volt. That's our new voltage of our capacitor after inserting the dielectric. So the dielectric material will increase the capacitance when I insert it between the two plates, but at the same time it will decrease or reduce the voltage or the potential difference across the two plates when the battery is disconnected. All right. I hope you find these two examples useful, and hopefully see you with other videos. Thank you.